Hello everybody, welcome to the very first video lecture we're going to be doing. I plan on having a lot of fun because I'm sitting out here by the beach. I hope you're enjoying as much as I am. I'm obviously not green screened, so just ignore the fact that the clouds aren't moving and the water's not raging, even though you can hear it in the background. Clearly you can hear the seagulls, so you know I'm just relaxing here. Hopefully these things go relatively painless. We'll definitely see, right? I think it all depends on what we make out of it. So this is basically going to be the general format. This is the best quality size situation I can get going. But we're going to be talking about second order differential equations. It's going to be a little something of a, what's the word I'm looking for here? Review. But to start here, moving forward, we're going to have documents like this that are going to be dated and put up in Moodle, so you know when the material is expected for you to know it. You should have done the reading before you watch the videos, and then watch the video by the date that's listed on them. Okay, I'm going to give you problems to do. They're going to be due 1 week after I assign them, and so hopefully that'll keep us regularly informed and the whatnot. And I will be figuring out some sort of daily time slots for where we can do Zoom meetings. I'm going to put some information, because a lot of us aren't familiar with Zoom, about how to join Zoom meetings and what it is. And so we can have a little bit of face-to-face time, okay? Now, these documents are going to go up before the videos, and the major thing is here that they're going to have the reading. All right, so here we've got Blanchard 388 to 399 and Logan 79 to 84. Pick and choose what you want to do. They're both good. You're not going to get the full treatment without reading both in some sense. But I think everything here is important. As a little son of my ass. Hold on a second. Let's just get this in. So to recap, just a very important point. The homeworks are going to be smaller, and they're going to be due weekly. So you're going to have an assignment every week, and hopefully you will get those back like the same week that you pass them in. So that'll be nice. You get the feedback. To do those, really, either do them electronically, like type them out, or write them out and take very nice pictures with your phone and upload them onto Moodle in the assignment. Okay. So as another sort of introduction to second order differential equations, because we have done this before, we do have constant coefficients. That's going to be a primary factor here when we're moving forward with our methods. So we've got the a, b, and c, which is constant. And in general, they're going to be non-homogeneous. So we've got some function f of t on the end. If it does happen to be 0, then we're at the homogeneous part. And I do apologize for my handwriting throughout all this. Vassar lent me a really crappy stylus. Hopefully I'll be getting a better one soon. And these things are second order because we do have the second derivative on the x term there. So as we can see right here. Now, equations of this form usually come from physics applications, which you should know is not my bag, but in physics, one of the fundamental laws there is going to be F equals ma. Something we should all be roughly familiar with, but just to kind of recap, F is a measure of the total forces acting on an object or within the system. Okay, mass is the mass, m is the mass of the system. Not the system, the object that it's acting on. And a is the acceleration of that object. Okay, so you might be wondering right now, like, how do I get from something like ax double prime plus bx prime plus cx equals f to f equals ma? Well, if we let x represent the position of the particle or object, then x prime is its velocity, and x double prime is its acceleration. Okay, you take those sort of distinctions right there, you plug them back into f equals ma, and then basically you're going to be arriving at an equation which looks at least a little bit more similar to what we have on top. We have mx double prime, and then we've got this big f of x of t. So really, like, as a function of x, that means you can be a function of its derivative and etc. But that's just really like all the other forces that are acting on it. And so we've seen a couple examples of these forces. A spring force or a restoring force is, typically speaking, proportionate to the position of the object, you know, because if it's really far away from the spring, there's a lot of force acting on it, and if it's at rest, not a lot. Really compressed, there's a lot of force wanting to push it out. Damping is another example where we are going to be proportionate to the forces, proportionate to the velocity of the object. So the faster something's going, the more air resistance is hitting it, or the more friction or drag that's acting on it. So that's an example there. And then finally, you have these examples of like driving forces, something that's not the object itself, but is moving the object. So like a motor or like a flow of water, or you're blowing air on something. And we're just going to represent that with a little f of t. Take all three of those dudes, add them up together into big F, and you basically get the general form of the equation. So to solve these, to start off with, we have to go over what's called the extended linearity principle. Okay. Now you might be wondering, like, where did the A, B, C, and F go in the other equation? Well, you take your A and you divide it out. So you get a B over A, a C over A, and F of T over A. You just relabel those P, Q, and G of T. You get something that's a little nicer to work with. We're going to label that red. That is our full second-order differential equation. Okay? And so to deal with that sort of directly, it's a little complicated. It's a big, hunky thing. We need to consider a subset of that problem called the associated homogeneous, which we're going to label green. It's going to be green from now on. Okay. Now, the associated homogeneous problem is found really simply by just taking that g of t and setting it equal to 0. Okay, so you get an equation that's very similar, like the dynamics are really, really almost the same. You still have got all those endogenous, the drag, the restoring forces, but you don't have the exogenous forcing terms anymore. So now let's suppose that x of p solves the full problem, okay, and we have some x of h that solves the homogeneous problem. Okay? Then what we can conclude is that their sum, x of p plus x of h, solves the full problem there. Okay? That's one simple fact that we can prove. We're going to have a video that's much shorter, about 6 or 7 minutes on that later. Now, the second thing is, if you suppose that x of p and x of q both solve the full problem, then their difference only solves the homogeneous problem. These two facts are really critical to putting this whole thing together. Right? First fact basically says, if you have any solution to the big problem and a solution to the little problem, okay, then that little problem is not really contributing anything that violates the problem when it's being forced. Okay, so you can take any sort of x of p, add to it x of h, and you still have the basic dynamics, because the basic physics of the object is still being observed. That px prime qx is just exogenous forces are not being covered. The second thing says, if you have two dudes that solve basically the full problem, but they're different, the only thing that can exist in their difference solves the problem without the exogenous forcing. Okay, and that's really interesting, because now we have two pieces to this puzzle that let us piece something together. And that if we have x sub, and I wrote capital H just for grins, if it's the general solution to the homogeneous problem, so any solution to the homogeneous problem is a special case of that. And you take anybody that solves the big problem, then when you add them together, that gives you the general solution to the big problem. Nothing's missing from that. Every other solution is just a special case of that. And I think I spend too much time when I'm writing figuring out the interface, so my lines are a little lagged, but that's okay. And so piecing these things together, really understanding this, tells us about our method of solving these differential equations, which is really important. Now, this should be a roughly familiar recipe to us, okay? And so I've done it in sort of like a blue box format here. This will be something that'll be useful for you to have, to look at, to think about, okay? But we see we have our general. That's a god-awful arrow. What am I doing? Get rid of that. Okay, better arrow, please. Okay. We've got our general non-homogeneous constant coefficient second-order differential equation. Hooray. Okay. Now, the first step in solving this, what we found is that a key to it is that we need to know what the homogeneous solution is. It exists everywhere. Okay. And so what we got to do is we got to find the associated homogeneous problem, which is really just by taking that g of t up there and setting it equal to 0. Then what we do is what's called the ansatz solution. Okay, and what that's going to give us, it's really powerful. First off, we presuppose it's a solution, but also it's going to give us something called the characteristic polynomial. So we suppose x equals e to the lambda t, and we plug it in to the homogeneous problem. What we get is lambda squared e to the lambda t plus p times lambda e to the lambda t plus q e to the lambda t. And that's going to still equal 0 because we want it to be the solution. Okay, so we're presupposing it's the solution. And now we have to figure out what lambdas make us not liars. Okay? We're going to cross out the e to lambda t over every term because it never equals 0, so we don't have to worry about dividing by it. It's gone. And what we're left with is something that we should be comfortable with, a polynomial. Critical here, the problem has given us a p and q. What we're going to assume we don't know is the lambda. Okay? This quadratic is known as our characteristic polynomial. And if we find the lambda that satisfies our characteristic polynomial, we found the lambda that is actually the solution to the homogeneous problem. Okay? Now, in solving for lambda, we're basically going to use the quadratic formula in order to, rather not in order to, but what we should know is that we get two solutions because it's a second degree polynomial. So we get negative p plus or minus the square root of p squared minus 4q, all that stuff over 2. Okay, so we have two solutions because we get the plus or the minus. So I'm going to call them lambda plus and lambda minus. And we have several different cases of this depending on the value in the discriminant, the thing I just highlighted in red there. If p squared minus 4q is positive, then we have two roots, they're both real, and they're not the same thing, right? Because you've got a number plus a number, and a number minus a number. That shouldn't be the same thing unless what you're adding and subtracting is 0. So we have two distinct real roots, lambda plus, lambda minus, they're both real. We've kind of gone over this in course already, so this is a recap. We can write down our general solution to that homogeneous problem as x of h equals some constant c1 e to the lambda plus t plus c2 e to the lambda minus t. I don't want us to confuse that with lambda plus t. It's lambda sub plus t and lambda sub minus t. Okay? And that is our solution in that case. Now what can also happen is that discriminant there, like I just said, that could be 0. The p squared minus 4q could equal 0. And if that's the case, then we're essentially running a repeated root. Right? So we can write down c1 e to the lambda plus t, but what we don't want to write down is plus c2 e to the lambda minus t, because the lambda plus and lambda minus are the same in that case. And so we're just writing down something that's already a multiple of it. So what I said that we do, that we've gone over before, is that you write down c2 t e to the lambda t. That's ugly, so we're going to rewrite it there. And it's a little bit of a mystery, I think, at first, where the hell that t comes from. It does make the second term not a constant multiple of the first term, but why do we know it works? Well, you can shove it in and show that it is indeed a solution. That works, but we'll do another short video covering where does that t come from in a rather natural way, so that way you guys can get maybe a better feel for that. That's going to be another like 6 or 7 minute video right there. Okay. Excuse me. The last situation here is when p squared minus 4q happens to be negative. If that's the case, we have complex values, and we did a whole big thing in class, complex valued solutions to real valued solutions, Euler's formula to take e to a complex number, make it sines and cosines. But you get c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. And the alpha and beta come from, when you look at that root, you break it down into alpha plus or minus beta I. All right, and so I think we can pretty much figure that out, but the alpha is going to be negative p over 2, and then the beta is going to be the square root of 4q minus p squared over 2. Always kind of how it turns out. Okay, and so now we've got basically 3 different forms that our general solution to the homogeneous problem can be. And I've already violated the thing. I just noticed now that I'm highlighting all this in red, and I should probably be doing it in green, but c'est la vie. Okay. Step 2 is we're going to use the method of undetermined coefficients to find a particular solution. So anything that happens to solve the big equation up top. Okay. And so we're going to basically guess some function big G of t, which is of a similar form to little g of t. You plug it into the problem, supposing it's a solution, and you can have a bunch of undetermined coefficients, and then you have to find what are the numerical values for those coefficients that make me not a liar. At the end of the day, you take your answer from part 1, your answer from part 2, and you add them together, and that's your general solution to the big problem. So every other solution that happens to solve the big problem is just a special case of that. I think right now it might be useful to probably do a couple examples here. So I believe I've picked 2 examples for us to do. One of which is relatively straightforward, and one of which is just a little bit more involved. It takes me forever to write, so we'll get there. And the first example is x double prime minus x prime, write the prime, there we go, minus 2x, or 12x, excuse me, equals 0. As you can see, I'm kind of reading off of this because my notes are down here and it's all a mess. There's beach sand all over the damn thing, okay? What's nice about this is our g of t right there is 0, so we're already at the homogeneous problem, so we don't need to worry about step 2. We only are going to have to do step 1 because the particular solution doesn't matter in this case. All right, so that's nice and useful. So what we do is that we suppose that x of t equals e to the lambda t. That's our ansatz solution that's going to give us the characteristic polynomial. We take that, we plug it up into there, we get lambda squared e to the lambda t minus lambda e to the lambda t minus 12 e to the lambda t. And that should all equal 0 because we're presupposing it's a solution, and we're going to find out what the lambda values are that make us not liars. Cross out those e to the lambda t's because they're just a complication anyway. We'll have lambda squared minus 12 equals 0. The only thing that's unknown is the lambda. We use the quadratic formula. Okay, so lambda is going to equal 1 plus or minus the square root of 1 minus 48, plus 48, excuse me, all over 2. 1 plus 48, I hope we understand, is 49. The square root of 49 is 7. So we have 1 plus or minus 7 over 2. So we have 2 answers here, 8 over 2, which is 4, and negative 6 over 2, which is negative 3. Okay, these are our eigenvalues for the problem. I'm just going to throw that word out right there. Okay, and we're going to be able to use those as our lambdas to put together into the first form. I don't know why I'm pointing with my left arm. That's freaking stupid. It's over there. So my solution here, x sub h, but it's our total solution, so we just write x, is c1 e to the 4t plus c2 e to the negative 3t. To find c1 and c2, we'd have to have initial conditions on either position and velocity or something that affect just 2 points that nail down where we are so that we can find those. So there, ta-da, we have our solution. That's relatively straightforward because it only dealt with basically 1/2 of the full blossoming, solution method. So now we're going to get a little bit harder. X double prime plus 2x prime plus 5x all equals, I think I put t squared plus 1. That's what I put. Okay. Go Ice Eagle. All right. So we have a non-homogeneous part here. We've got some external forcing. That may make us sad because we do a little bit extra work, but we can proceed with step 1, like we did before, with solving the homogeneous. Now, I'm doing a little bit of extra writing here. Most of the time, you're just going to look at that and know to write down the characteristic polynomial. There's my homogeneous problem. I'm just going to write down the characteristic polynomial as lambda squared plus 2 lambda plus 5 equals 0. So basically lambda to a power is equivalent to that power, the derivative of the x. And so lambda, the quadratic formula, is negative 2 plus or minus 4 minus 20 all over 2. 4 minus 20, negative 16. The square root of that is 4i. Right? It's negative. So we're going to have complex values. So it's important for us to pay attention. We have negative 1. Oh yeah. Negative 2 divided by 2 is negative 1, and 4 divided by 2 is 2. That second 2 right there, that's an I. Let's just be real. And so our alpha is negative 1, and our beta is 2. So our homogeneous solution ends up being c1 e to the negative t cosine of 2t plus c2 e to the negative t sine 2t. I'm not making these 20-some-odd minute videos anymore. I need a Mai Tai. I need something to drink. That's what's drive. Thank you, sir. It's all paid for by the vacation. So we have the homogeneous solution right there. It's beautiful. It's all put together. We now need to move on to step 2, which is the method of undetermined coefficients, which is very similar to what we did in one dimension. In fact, it's pretty much the same thing. So we see there we have a quadratic, t squared plus 1. So I need to suppose a quadratic. So I'm going to suppose a t squared plus bt plus c. All right. Now, you might be asking, why am I supposing so many extra terms? As a rule, when you identify what type of equation is highlighted up there in orange, you want to pick the most general version of that. So that a t squared plus bt plus c is the most general version of a quadratic. We take its derivatives to get 2at plus b and 2a. Now we take these three functions right there and we shove it up into the original problem. Okay, it's going to be a lot of writing. Bear with me. That straight line, I don't know what caused it. No idea. So we get 2a plus 4at plus 2b plus 5at squared plus 5bt plus 5c. Okay, so that's all of it. Now that's the left-hand side. That needs to be eventually equivalent to the right-hand side, right? That's the whole point of it, is that we have come up with some sort of quadratic that is equivalent, all right? So then we look, where do all these terms come from? The x double prime is just the 2a. The 2x prime, you notice I took 2 and multiplied it by the expression we had there. And then the 5x, why that's all covered down there in 5 times the original expression that we had for xp, the assumption we had. Let's group this, let's cluster it up by t, because the right-hand side, t squared plus 1, that is naturally clustered by t. So we're going to do the same sort of thing. So we have 5at squared. That needs, oh, whoops, plus, I skipped a step. My bad. Plus 4a plus 5b times t. Those are the 2 extra terms there that have the t's on them. And then plus 2a plus 2b plus 5c. And this should all be the same thing as t squared plus 1. All right? And so you might be like, but we don't have a t on the right-hand side. Well, that's a very good point. And that's actually the point. We have a 0t over there. And so we have a 1 in front of the t squared, a 0 in front of the t, and a 1 all by itself. So we're going to take those terms that are kissing the various t's and make them equivalent to one another. So that 5a is equivalent to the 1 in front of the t squared, so we get 5a equals 1. Solving that's, I hope, relatively simple. We get a equals 1/5. Okay, I did not pick numbers to be particularly pretty. This one's a little bit ugly, but we've got 4/5 now because I did the 4a, plus 5b needs to equal 0 because the number that's in front of the t on the left-hand side is 4a plus 5b, and the number that's in front of the t on the right-hand side is a 0. Okay, solve this for b by moving the 4/5 over and dividing by 5. We are going to get negative 4/25 is the value for b. Like I said, they're not too ugly, but they get a little out of control. All right, we've nailed down a, we've nailed down b. What we're left to do now is to figure out what the value for c is. So we have 2/5 minus 8/25 plus 5c equals 1. And so what I did there was I obviously plugged in the value 1/5 for A and negative 4/25 for B. Now I'm going to come up with a common denominator here. So 2/5 is the same as 10/25. Add those two together, you get negative 2/25. Push it over, divide by 5, you get negative 2 1/25. Right? So we have now the A, the B, and the C that were in our original guess in the dark green there, that make us, in a very real sense, not liars. Okay, XP is a solution to the original problem if that is my A, that is my B, and that is my C. Why do I know it's a solution? Because I plugged it in and did the work. All right, so our final solution then is going to be the sum of the homogeneous solution we found and the particular solution we found. Okay, homogeneous solution we found was the trig thing. So we have c1 e to the minus t cosine 2t plus c2 e to the minus t sine 2t. And then what we're left with here is 1/5 t squared minus 4/25 t minus 2 1/25. I kind of run out of room here, so we're going to go to the next line there. I should put my camera on top of the notes. We're learning this all together. It'll be fine. I'll get my team to do it. That work? No, it didn't. Thank you guys very much for joining me in the first video. I hope this helps. Stay tuned for some more, okay? Bye. I said bye.